Now we're going to move to percent yield. But to first do that, I'm going to illustrate the very last one of these. How many grams of mag oxide? Where does my box go? There's mag oxide. There's my grams. That's what I'm looking for. Can be formed from the combustion of 42 grams of magnesium. Okay, I know this is 42.2. How are we going to get there? This should be pretty easy. I'm going to go, I'm going to go what? Box equals star. I'm going to go from grams of this to moles of this, from moles of this to moles of this, from moles of that to grams of that. It's no harder than that. Box equal star. From grams of magnesium to moles of magnesium. From moles of magnesium to moles of mag oxide. From moles of mag oxide to grams of magnesium. You've arrived at your destination. You multiply that out and you get 70 grams. In this case, 70.0. Okay. By the way, how did I get the conversion factor to go from here to here? I got that from what? What's it called when you go up and down? It's called molar mass, and you always get the up and down from grams to moles from the periodic chart. And that's molar mass, which we know from chapter 2 is just given the symbol A. How did I know there was 1 mole of this for every 1 mole of that? How do I get the relationship between moles of something to moles of something else? That is the stoichiometry. That's your balanced chemical equation part. Oh, by the way, I did this wrong, didn't I? Hey, look at this. It's still going to give me the same answer, but look, this should have been a 2, and this should have been a 2. Boom, caught myself. See that? It says for every 2 moles of magnesium, you're going to get 2 moles. If I'd been asking about oxygen, what would it have been? For every 2 moles of magnesium, I get 1 mole of O2. Okay, but in this case, it was mag oxide. And then how do I come out of this mole hole? Again, I use what? Atomic mass or molar mass. And where do I get it? Periodic chart. Okay, so there we go, 70. So this is what takes us to the next topic, which is this. This is the theoretical. I calculate I should get 70 grams in a perfect world. Okay, and as we know from all this virus and all that kind of stuff, this is not a perfect world. But remember, we just calculated this. This is a calculated value. This says if I do everything perfectly in the lab, I should get 70 grams. But guess what happens? Guess what happens if some of this magnesium reacts with nitrogen in the air? Ooh, guess what? As I lose some magnesium this way, what's going to happen here? This number is going to be smaller in the real world. Not my calculator, but in the real world. So usually we have a divergence between what we calculate, which is also called the theoretical value. Oh man, my computer is going to be really slow because I'm doing a lot of recording here. Okay, so this is the theoretical value. So let's take an example in the real world of where we run this very reaction and we don't actually get 70 grams. We find out when we go to our lab and run our experiment, we only recovered 33.7 grams. How did we do? Well, that's called yield. Sorry, I'm trying to get rid of this value there, that thing. Okay. I was trying to clean this up and it is not going to let me. So let me just move that back. Okay. So what is percent yield? It's your experimental amount. That is how much you actually recover. Some textbooks will call this the actual amount. Some will call it the experimental, as I've shown here. Some might call this the lab. Okay, and the theoretical. Sometimes this is called the theoretical, sometimes it's called the calculated amount. I kind of like the calculated amount because why? That is what we're going to do. We're going to calculate that using our stoichiometry calculations times 100. So again, this is part. What's the part? How much we actually got. What's the whole amount we could have got? The theoretical. So for those of you who have learned anything that's percent is parts over whole, that's exactly what this is. It's the whole amount I could have got divided by the parts I actually got. Okay, so here it is in Jasper speak. Yeah, it's what you got over what you should have got times 100. There we go. So let's now work this problem that we have. For the magnesium reaction above, that's this, the one in which we calculated 70. For the reaction, if you actually recover 33.7 grams of mag oxide, what is your percent yield? Well, since I can't type, I'm just going to have to show you. We'll work it out. Okay, the percent yield is equal to experimental. What was our experimental? 33. Over the theoretical, let's see, our experimental was 33 grams. Over our theoretical, what was our theoretical? Our theoretical was 70 grams times 100. And there's your 3. So when you multiply those out, you wind up getting 48.1%. 3 sig figs, that's exact, so 3 sig figs. 48.1%. So how'd you do? Well, I thought I was going to get 70 grams, but it looks like I went in the lab and I only got about half as much as I could have. Okay, that's reasonable. Guess what? I don't know. Who knows why you did it? That's a different question. But what you got, how far you got from this, could have been done to a number of things. Maybe a bunch of the nitrogen in the air took some of your magnesium away that you needed to make mag oxide. That's reasonable, after all. Air is about 79% of this and only 20% oxygen, so hey, that could have been a problem. The other thing is, you might just be a lousy chemist, or who knows? Maybe you thought you put 42.2, but you spilled some, and you really didn't have 42, so you couldn't get 70. We don't know. What happened, whether it's Mother Nature and there's a legitimate reason, or just poor technique, we don't know. But one thing we do know is, we only got half as much as we theoretically could have. Any questions on percent yield? Those are pretty simple. The key is to know that this experimental value has to be given in the problem, or else it has to give you some data where you can figure it out. And the theoretical is your gram to mole to mole to gram type of calculation. It is your stoichiometry calculations. So really you should just look at percent yield as just a derivation of stoichiometry type problems and not as something drastically different. Here's just an example of what this would look like if you bundled them all together to make a type A type of question. So from the combustion of magnesium to give magnesium oxide, you start with 42.2 grams and you end up with 33.7 grams of magnesium oxide. What is your yield? So if I gave you this just from scratch, you would have known the first thing you need to do, and let's analyze it right quick. From the combustion of magnesium, you start with 22, Control Z. Oh, now this is really behaving. So you would start with the 42.2 here. And you end up with 33. Here's what you don't want to do, 33.7. Now this is true. You wind up with 33.7 grams. But what do you know? You better circle it or do something different. Why? Because this is what? It's telling you this is your experimental. You still don't know what your theoretical is. Right, so this is what you need to see when all these are jumbled up. All the information is jumbled up in one problem. And you end up with 33.7 grams of mag oxide. What is your percent yield? So what would you know that you need to do? You need to calculate your theoretical yield from grams of this to moles of that, from moles of that to moles of that, from moles of that to moles of that. To grams of that. And so There's your flight path redone again. So you would have done this and calculated your 70.0. And you're clever enough now to know that this is actually your theoretical. And now what do you have? Now you have enough to fill in here. You have your experimental value. You have your theoretical value. And you have your experimental value. And you can now calculate your percent yield.